All right, pre-calculus students, welcome back from the break. I hope you had a good rest. And let's get straight into it. This is lesson number 1 of Unit 5, Polynomial Functions and Optimization. And our focus for today's lesson is going to be on quadratic functions. Please do not make the mistake of assuming that you know everything about quadratic functions. As you've experienced in pre-calculus before, we take concepts that you're familiar with and we show you new applications and delve a lot deeper into applications and nuances and subtleties. Okay, that being said, the warm-up should be something that you're familiar with, and so we have a quadratic function f of x, and we are going to put it into vertex form. And we're going to do that by completing the square. So I'll give you a very quick reminder. In order to complete the square, make sure that the coefficient of the squared term is 1 and maintain the balance of the equation. So let's get started straight away. What I'm going to do is I'm going to move the plus 5 to the left-hand side. This is not required. This is just my preferred method of approaching the problem. And the next thing you want to pay careful attention to, two things. So I've taken the plus 5 and I've moved it to the left hand side. The second thing I've done is I've factored out my 1/2 from these two terms over here, and so if I were to distribute back, I would go straight back to half x squared minus 4x. Okay, so the next thing I want to do is to actually complete the square. Identify the b value, divide it by 2, square it, and add it to both sides, but there's a small caveat there. So minus 8 divided by 2 is minus 4, squared is going to give me plus 16, and not plus 16 on the left hand side. Instead I will be putting in plus 8, and that of course is because 1/2 times 16, in fact I was only adding 8 to the right hand side, and therefore adding 8 to the left-hand side and keeping the equation balanced. Okay, I'm now in a position to continue. So I have f of x plus 3 is equal to 1/2 x minus 4 all squared. And we can see from this form, of course, f of x is the same thing excuse me, as y. And so we could also write this as y plus 3 equals 1/2 x minus 4 all squared. The vertex form of the equation of a quadratic function, which allows us very easily to identify the coordinates of our vertex, which are in this case 4, minus 3. Okay, which of course will help us with the sketching of the graph. Axis of symmetry. The axis of symmetry is the vertical line that passes through the vertex, and so our axis of symmetry is going to be at x equals 4. This is the fold line of the quadratic function. If you were to fold along this line, the two branches of the parabola would match exactly. Okay, and we have our turning point, our vertex at 4 minus 3. Since the coefficient a, the lead coefficient, is positive, of course this quadratic is going to open up. And so our axis of symmetry, x equals 4. And now we have to sketch our graph. In order to sketch the graph, we're expecting, in this case we have the vertex graphed. We would want at least 2 more points. And so what we could do really easily in this case is we could go back to the original equation over here, make x equals 0, and find our y-intercept, which is going to occur at 0, 5, and then use the symmetry of the function 1, 2, 3, 4 away. So if I go 1, 2, 3, 4 away on the other side, I will have the points, and I can then go ahead and join that and finish my graph. In this particular case, not very well done. Let me just try that again. Put that point back. Okay, slightly better. And of course, in this particular case, however, we've specifically and expressly been asked for the x-intercepts, and so even though I haven't shown them on my graph, I'm going to go ahead and find those. So what I can do to be efficient is I'm going to use my vertex form of my equation in order to find the x-intercepts. The x-intercepts where we cut the x-axis, which of course occurs where y is equal to 0. And so I can equate y to 0, and I'm looking at the following equation. I'm going to move the 1/2 to the other side, so 6 is equal to x minus 4 all squared. I'm going to square root both sides of the equation, and in so doing, I must remember to introduce a plus minus. And then my final answer, 4 plus or minus the square root of 6. Square root of 6 is, of course, more than 2 and less than 3. And so if we say 4 plus 2 and a bit, then you can see that explains the x-intercept just to the right of 6, and vice versa for the other x-intercept. Okay, little warm-up, little review, hopefully not too much of that was new. Okay, the unit really is focused on polynomial functions, not today's lesson, just the unit as a whole, and so I'm not going to focus too much on this. Suffice it to say that the polynomial functions we're interested in must be continuous functions, no breaks, no gaps, and no holes, and they are also not the most mathy language, but no pointy bits either. And so if we are going to identify which of the following graphs in example number 1 represent polynomial functions, hopefully it's clear to you that B and D are the two. A is not, because we have a break in the graph, a discontinuity, and in example 1C, we have one of our pointy bits. And so later on, when we get into limits and you start to understand the basics of calculus, you'll understand why we cannot have points in the graph like this. The functions are not differentiable at these points. Okay, so let's move into the different forms that the quadratic function, that we can use to represent the quadratic function. And I'm going to use y equals notation, but of course I could just as easily use f of x. It doesn't matter. We're going to treat those as interchangeable quadratic functions. These are all functions in the form that we're giving. And so the general form is going to be ax squared plus bx plus c. Our intercept form, or zeros, or x-intercepts, or roots, they're all the same thing. It's where the function cuts the x-axis, where y equals 0, and so that's going to be in the form a times, and I'm going to use x minus b and x minus c, where b and c represent the x coordinates where the function passes through the x-axis. And then the vertex form is the one we just used when we completed the square, a times x minus h all squared plus k, or the version of this that I prefer, y minus k is equal to a times x minus h all squared. We would accept either one of those, whatever your preference is. Okay, of course, the vertex form, and so we've got the different forms because each of the different forms is going to allow us to solve different kinds of problems. So some forms are more useful for certain kinds of problems, and hence the reason that we need all three different forms of the function. Okay, so in this case we're going to describe the transformations in the correct order, and so I'll just remind you as a general rule, when we deal with transformations of functions, you will know to use RST, which is reflections, stretches, and translations. I'm going to modify that to RDT, reflections, dilations, and translations, generally speaking in that order. Okay, and so we have the function f of x, which is x squared minus 1, and so keep in mind that that function has already been transformed, and what we've been asked to do is to describe the transformations that get us from the f of x function to the g of x function. And so the first thing we're going to do is put each of those functions into vertex form. The vertex form is the form that allows us most easily to see transformations that have occurred. And so my suggestion at this point would be to pause the video and go ahead and do the completion of the square yourself and see if you can do those transformations. I'm going to either that or do it while I do it, as opposed to just being passive and copying down what you're seeing. Okay, so I'm going to go ahead and do that, and then I'll talk you through some of the details. So I'm going to do it for both of the functions. Okay, so we have f of x plus 1 is equal to x minus 0 all squared. I'm including some details you probably don't need, but I'm just going to be a little more explicit. Okay, and then we have g of x minus 7 is equal to 3 times x squared plus 4x. Complete the square there, so that's going to be a plus 4 over here and a plus 12 on the left hand side, to account for the fact that it's adding 4 on the right inside the parentheses is in fact adding 12 to the overall equation. And so now I have g of x plus 5 is equal to 3 times x plus 2 all squared. And so now what we are able to do is look at our two graphs and compare the corresponding parts. So we had f of x plus 1 and we've got g of x plus 5. We have x minus 0 all squared, and we have x plus 2 all squared, and last but not least we have our a value, which isn't represented, of 1 versus an a value of 3. And so this should make it fairly clear what the transformations of the graph are. And so to begin with, number 1, we have got ourselves a vertical dilation by a factor of 3, and we have then got two translations, and so we have got a translation 2 left and 4 down. Okay, and so what I'm doing is I'm saying this graph has already been transformed from the parent graph of y equals x squared. It's already been transformed 1 unit down. I'm now going a further 4 units down, hence the 4 down. This was not transformed at all in terms of horizontal movement and has now been translated 2 units to the left, hence the 2 to the left. And then RDT, of course, first I'm giving the dilations and then the translations. Okay, now we move on to example number 3. What we have here is the first of our application problems, and so this relates to optimization. And so we're dealing with polynomials and specifically optimization of those polynomials. Okay, pay attention to our details here. So we have a farmer with 60 meters of wire, and that 60 meters of wire is going to create a rectangle, or rather 3 sides of a rectangle. If you remember anything from geometry, you'll remember that a rectangle is a parallelogram and therefore has opposite sides congruent. And so we are told that BC is x. This leaves us with 60 minus x meters of fencing for sides CD and AB, and of course those are equal, so we're going to divide that by 2, and we're going to have a length of 60 minus x over 2 for each of the CD and BA sides. Okay, equation for the area of the rectangle, area of course length times width, base times height, either way. And so our area, A of x, area in terms of the variable x, will be x multiplied by 60 minus x over 2. Hence find the dimensions of the enclosure that will maximize, and so hence the optimization problem. And here we're going to avoid using calculators. Fortunately, what we have here is we have got our intercept form of our function, and so what you should be able to do relatively easily would be to sketch a graph of this. We of course have got intercepts or zeros at 0, and our second intercept is going to occur when 60 minus x over 2 equals 0, i.e. where x is going to be equal to 30. I beg your pardon, where x is going to be equal to 60. And then we of course have our negative x squared coefficient, and so our function is going to open down. Of course the function does exist in the other parts, but for the purposes of practicality, those aren't practical in terms of a domain. If we find our midpoint, which is going to produce our vertex, that of course will occur at x equals 30. And so x equals 30 will produce the maximum possible area. This is our area function, and so we have 30 comma whatever this is, which is going to produce our maximum area. The question that we have to answer is, what are the dimensions? Our dimensions are x by 60 minus x over 2, and so it's going to be 30 by, in this case, 60 minus 30, which is 30 divided by 2, 30 by 15 for our length and our width. Okay, example number 4. All right, so example number 4 is going to be, I think, a new challenge for most of you, or all of you. And so we need to pay careful attention. There's a couple of different ways of doing this, and I'm going to, it'll take a little bit longer. You can always fast forward the video if you've come across the method that you prefer. And so I'm going to do this in 2 different ways, and I'll explain each as we go. Okay, and so let me just take you through the problem really quickly. So we've got tickets for the high school production. The students have done some research. They find that if they price the tickets at $10, they can fill 1,300 seats. For each dollar increase, they're going to sell 50 fewer tickets, and we are looking to maximize our revenue. And once again, this is a non-calculator question. And so we're looking to use one of the forms of the function, specifically the intercept form, that's going to allow us really easily to identify the turning point, which is going to in turn yield the x value, which will yield the maximum. Okay, in terms of our revenue, essentially what revenue is going to be, the amount of money that we're going to collect is going to be the number of tickets that we're going to sell multiplied by the price per ticket. And so that's going to be consistent across both of the approaches that I'm going to show you. So the number of tickets times the price will give you the amount of revenue. And of course, the other layer would be to then look at cost and determine profit, but that's not our focus. Okay, so approach number 1. So let me just mark this off over here. Okay, so option number 1, what we're going to do is we're going to treat x as the price. Okay, and I'm then going to find a function that is going to represent the number of tickets that we sell depending on what the price is. And in order to do that, I'm just going to find the equation of a line. So what we already know is that if we've got our x as price, if the x-axis represents price and the y-axis represents number of tickets, I already know that I will sell 1,300 seats if the tickets cost $10. And so I'm going to just kind of estimate more or less if I've got that point over there. I also know that for each dollar increase, so if that price over there, so that's the point x equals 10, y is equal to 1,300, that the next point along the way, for each dollar increase, there's 50 seats fewer. So if I increase by $1, I'm going to decrease the number of seats, and the next point that I'm going to arrive at is going to be 11, 1250. This, of course, will produce a linear function, and if we can find the equation of that linear function, then that is going to represent the number of tickets that are going to be sold depending on what x is as the price. Okay, and so if I do that, so I'm going to do that pretty quickly. So what I've got now is I've got 1 point. So I've got this point over here. It's the point 10, 1,300. I'm using y equals mx plus b. I already know that my slope is minus 50 over 1. and the idea of the minus 50 over 1 is for each additional dollar. So for each additional dollar, I am losing, if you will, 50 tickets, the sale of 50 tickets. And so we have got y equals minus 50x plus b, which is going to be my y-intercept. I'm going to sub in the coordinates of either one of these 2 points in order to solve for b. And so in this case, I'm going to say y is 1300 when x is 10. And that allows me to solve for b, which is going to be 1800. My revenue function is now going to be x, the number of tickets being sold, the price multiplied by the number of tickets, which is 1800 minus 50x. Okay, and this is going to be one of the options for our revenue function. Both of the approaches will yield the same answer, which is the price that should be charged in order to maximize revenue. Okay, but keep in mind, in the context of this model, x represents my price, and 1800 minus 50x represents my number of tickets. Okay, so here's an alternative approach. In the alternate approach, what we're going to do is x is going to represent each dollar increase, or another way of thinking of it is x is going to represent incremental change. Okay, so then we can do it like this. The revenue is then going to be, I'm going to start off here. The first set of parentheses will represent the price. The second set of parentheses will represent the number of tickets, and we're just going to base it off the information that we already have, which is $10 and 1,300 seats. And so if the price is $10, for each additional dollar, the number of tickets, which starts at 1,300, is going to go down by 50. And so the advantage, of course, of this approach is that it allows us to get the function really quickly. It involves far less work, but again, intuitively, whichever one makes more sense to you, both of these will yield the same answer. Okay, and so let me just show you that very quickly. So if I go back to my first approach, what I have here is I'm just going to sketch my function. Okay, just move that down. All right, and so what we have here is we've got a 0 at 0. Our other 0, if we solve here, our other 0 occurs at 1800 over 50, which is at 36. And as before, our lead coefficient, the x squared, is negative, so the function is going to open down, and the midpoint, or the maximum, is going to occur where x is equal to 18. So in this particular case, that is the x value that produces the maximum. That is the price that we need to charge. So charging $18 produces the maximum revenue. So the function here was harder to obtain, but once we obtained it, it took us straight to the ticket price, which in this case maximizes revenue. And so that answers our question. What price should we sell the tickets for to maximize revenue? The answer is the price should be $18. Okay, let me show you that we get the same answer in the other problem. And so I'm going to go ahead and sketch my graph of the other revenue function. Okay, so. Okay, and so in this particular case, over here we have a 0 at minus 10, and the other parenthesis produces a 0 at 26. And once again, our function is going to open down. If we identify the midpoint of those two, so 26 minus 10 gives you 36, divided by 2 is 18 minus our 10, you can see that this is going to occur at 8, and so our maximum occurs at x equal to 8. But if you look carefully over here, the price function is in fact 10 plus x, which is 10 plus 8, and so once again we have a price of 18, which will produce the maximum revenue. And so even though the two functions are slightly different, they've produced different x values. Since x does not represent the same thing in each of the functions, we still get the same answer. Okay, so that's a lot to take in. I would suggest you use the approach which is more intuitively obvious for you. So option 1, x as the price, and use a linear function to determine the ticket number, and then the product of the two for revenue. The alternative is to treat x as the incremental price change and have it impact both the price and tickets in order to generate the revenue function. Okay, moving on. This should be a little bit of review again. And so we're talking about the roots or the zeros or the intercepts of the quadratic function. And we've got, with a quadratic function, up to 2 real solutions. And so 2 distinct real roots. In this particular case, you can see it's cutting the x-axis at 2 different places. Those of you familiar with or who use the quadratic formula, which is obviously a pretty effective way of solving quadratic functions, just for memory's sake, minus b plus or minus square root of b squared minus 4ac all over 2a. The part that can tell you which of the 3 options we're looking at is, of course, our discriminant, the value of b squared minus 4ac. Where that value is greater than 0, we'll get 2 distinct real roots. Where the value of b squared minus 4ac is equal to 0 is when we get a repeated root, and where the value of b squared minus 4ac is less than 0 is where we get our imaginary roots. And so I'll just give you a quick example of each of these. And so we might have, and again, this is one of the ways that's really useful if you think of all functions in terms of transformations. So the original parent function is, of course, centered at 0, 0. What have we done here? We've moved a little bit over to the right and a little bit down. And so an example, keeping in mind that we don't have any details from the graph, but an example of an equation which may be representative of the graph that we're looking at is something like y is equal to x minus 3 all squared minus 2, representing a shift of 3 units to the right and 2 units down. Similarly here, we don't have any vertical movement. We've just got a shift over to the right hand side, and so an example function might be y is equal to x minus 2 all squared, and in the third instance over here, an example function would be something like x squared plus 1, where we have just moved vertically, and as a result of that vertical movement, we're not going to produce real solutions to the intercepts or zeros. Okay, and so that is where a lot of our focus is going to be in this unit, and that is dealing with real and imaginary numbers which are subsets of complex numbers. And so all of the answers to the 3 graphs above are part of the set of complex numbers. Complex numbers consist of purely real, purely imaginary, and complex numbers which are a combination of a real part and an imaginary part. Okay, and so what you hopefully do remember, of course, is that where a polynomial has got an imaginary root, imaginary roots comes in what we call conjugate pairs, and that, of course, is as a result of the fact that the square root of the negative is what produces the imaginary solution, and based on the quadratic formula, of course, we have plus or minus the square root of b squared minus 4ac. Okay, so just a couple more examples to go. These should be a little bit of review, and so I'll go relatively quickly through these. So a quadratic function which has got integer coefficients, and so ax squared plus bx plus c, where a, b, and c are all integers. If it then produces a radical in the answer, then we know that the other root must be x equals 1 minus root 5, and that is going to, sorry, that's the answer to that question. That's going to allow us then to create our equation. So we've been asked to create an equation. Your note says standard form. That should say general form, again, just to be consistent with the forms earlier. So an equation in general form that represents all possible quadratic functions. And so we're asking for the general solution here, and so I'll show you what I mean in just a moment. So what we're going to do here is you've got a couple of different options, and so I'll give you a really simple example. If I had roots of 2 and 3, you would know that the function was x minus 2, x minus 3, and of course I would then need to know whether or not it had been dilated at all. In this particular case, the root is a little bit more complex, but the method is the same. And so option number 1 would simply be to use the intercept form. And so y is equal to a times x minus the first answer, 1 minus root 5, x minus the second answer, 1 plus root 5. And if you were to expand that out, you would get your general form of the equation. Okay, and so since I've written it out, I'm going to go ahead and expand that out. A little bit laborious, but just to show you, belabor the point that we do in fact get the same thing. So a equals x squared, and then we're going to have minus x plus x root 5. I'm going to switch colors here, and then we're going to have minus x minus, hold on, make sure I haven't made a mistake here, x squared minus, I beg your pardon, this should be, that should be a minus, and we've got minus x plus x root 5, and then lastly plus, and I'll do this a little bit slower, 1 minus root 5, 1 plus root 5 are the terms that are left. Okay, so y is equal to a times x squared minus x root 5 plus x root 5 are going to cancel, so that's going to give me minus 2x, and here we've got 1 minus root 5 plus root 5 is going to cancel, minus 5, and that's where we're going to get our minus 4 from. So again, really mechanical, really laborious, but it gets us to the correct answer, and so that's using the root method. I'm going to show you a far more efficient method, and that would be for us to essentially, so option number 2 is going to be to reverse the idea that we used earlier. We're going to reverse the solving. Okay, so what I mean by that is if I have x is equal to 1 plus or minus the square root of 5, I'm going to move the 1 over to the left-hand side, and then I'm going to square both sides. And so what I'm doing is I'm undoing the solving of this. I'm going to get on the left-hand side x squared minus 2x plus 1. I'm going to get on the right-hand side, sorry, that should be root 5, so I'm going to get 5 over there, and I'm going to get x squared minus 2x minus 4 equals 0. I'm going to reintroduce the y equals, because of course in order to solve we equate y to 0, so I'm going to replace the y and also introduce my a term, so x squared minus 2x minus 4 is equal to y, and the final piece that we need is to specify that a cannot be 0, and so we'll do that on both sides. So don't forget that it's an important domain restriction, otherwise the expression is not valid. Okay, and then the last piece of course is to solve for a. We're now given a specific point that we can substitute in order to find the specific equation as opposed to the general equation which we did in part B. Okay, and so subbing in, minus 6 is equal to a times, and we're going to put 2 squared minus 2 times 2 minus 4, and a ends up being 3 over 2, and our final answer, f of x equals 3 over 2 x squared minus 2x minus 4. No need to distribute. Okay, moving on. Last one. This example is in terms of method identical to the one I've just completed. It just involves an imaginary solution, but the process is absolutely identical. So once again, option number 1, f of x is equal to a times x minus 2 minus I, x minus 2 plus I, and distribute all of that out, which you saw from the previous one was fairly painful, and so I'm going to avoid that approach. In this case, I'm going to use the reverse solving instead, and so I'm going to say x is equal to minus 2 plus or minus I, x plus 2 is equal to plus or minus I. I'm going to reverse the solving by squaring both sides. X squared plus 4x plus 4 is equal to minus 1. Remember, the square root of minus 1 is equal to I, and therefore I squared is minus 1. And so that's where that's been obtained. And so x squared plus 4x plus 5 equals 0. We're now going to put it into the form that we need. Y is equal to a times x squared plus 4x plus 5. Substitute in for our given point. 13 is equal to a times minus 7 squared plus 4 times minus 7 plus 5, resulting in an a value of 1/2 and a final answer of f of x equal to 1/2 x squared plus 4x plus 5. Okay, and so ends the rather long video. Holiday's truly over at this point. A couple of